Hey everyone, my name's Saul. I work at Quantsite, and today I'll be talking about a project I've been working on for the past year or so. It's pretty experimental and more of an idea at this point than something you can go download and make your life better. So if that's what you're looking for, I won't be offended if you leave halfway through the presentation or right now. But I wanted to present it here. Oh yeah. Sure. But I wanted to present it here just to get some feedback from other people, and also because this is a library marketed towards other people making libraries in Python. So this is not something necessarily an end user would, it would be useful to them, but it's more for other people making libraries like pandas or ibis to help those kind of libraries work together. So before that, I'm going to start with a little narrative. And so it starts with, how do we make our code faster? So can everyone see this? So the other thing is that we have a pretty small group here, so if there are questions or comments halfway through, feel free to just raise your hand, and we can get to them as I'm presenting. So we have this code in Python. It's iterating through a loop. It's doubling every item in that loop, and then it's indexing. And it takes some amount of time, and we might want that to go faster for our application. So what are some ways that you could speed up this code? Any ideas? Generators. OK. So changing the code so that it goes quicker.
You could combine them into one, so just I plus I into X.
OK, so maybe less operations that are happening in the end. Use numba, right? So we look at the whole program as one, and then we kind of compile it. So overall, there's there's kind of two strategies here. One is we could make the code faster through some optimizations, or we could just get better hardware, right? We could get a faster CPU. So first, let's look at how we'd make the code faster. So the classic way, not using numba or anything fancy, would just be to switch to NumPy, right? And so we have some pretty similar code, but it runs a lot quicker. And it runs quicker because each instruction basically is running less instructions on the CPU, right? And maybe it's allocating less memory. So this is besides tools like numba, this is sort of classically how we'd get better performance in Python, is writing tools like numpy and scipy and pandas. And they call out to write C libraries instead of doing everything in the Python interpreter. So this kind of mental model of how to speed up Python is built around the von Neumann architecture. So this is the architecture of your CPU, but it's also the architecture of Python itself, right, as a model. So for this code to run, if we look back at this code, what it's doing is it's fetching, fetching something from memory, it's executing some instruction on it, then it's saving that back in memory. So if we look at our CPU as a little unit that's doing this, we can look at Python as like a isomorphism of that CPU, but at a higher level, right? So maybe we're not dealing with bits anymore, but we're dealing with larger blocks of memory, and it's still a very much sequential process. Then when we switch to something like numba, like you mentioned, that's kind of inverting this, right? We're not speeding it up by making this particular line faster. We're speeding it up by looking at the whole program as a unit and optimizing it. So that's some of the difference I'm going to be talking about today. But if we look, so many of our languages today are von Neumann based, right? Like Java, JavaScript mainly. The only time so some that aren't are like SQL, right? Or if we use more functional kind of programming techniques, where instead of keeping everything as a sequential list, we're looking at optimizing the program as a whole. And so how does this relate to where we are in Python? It relates because there's been a change in how hardware has been improving. So if you see here, this is the transistors are still going up exponentially. right? So this is Moore's law saying that we'll have exponential growth in the transistors, but the frequency here has kind of plateaued in the past, I don't know, 10, 15 years. So what this means is that if we use our von Neumann kind of architecture of Python, which is like make all the, use less instructions if you can by using something like NumPy, and get faster CPUs every year, and things will just get better, right? This is kind of the world we've been in. This is ending, or it has ended. So we can no longer depend on running through this sequential model to make our programs faster. Instead, what we see here is we're seeing an increase in number of cores. So we're moving from a model that is just one CPU to possibly many CPUs. And even more than that, so I have some physics here, but I don't really understand the physics, so I'm not going to explain it. But there's some laws about computing scaling and blah, 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 thermodynamics. I don't know, things get too small and then you can't make them faster or something like that. But the end result is the plot, basically, right? The CPU frequencies aren't going up. But, so we don't just see like that we're getting multiple CPUs, we see other kinds of optimizations, right? Like pipelining in your CPUs. So instead of being the sequential process, really it's a parallel process now. It's just hidden from you as the user, right? Or caching at the memory level, right? Or things like GPUs or ASICs or FPGAs or other custom chips. The reason why we're having to move to those now is because we can't get the same performance on the CPU, which had this simple mental model, relatively simple mental model compared to these custom chips. So what this is leading to is that we have here like really an intellectual bottleneck about that we're thinking about our programs as, hey, I have some memory and I have some processor, right? And I want to, I need to be shoveling more bits back and forth to make it faster. And the issue with just thinking about how do we decrease maybe that one instruction to be, A range to be a NumPy A range, is that we're not really thinking about the whole process. We're just thinking about this one instruction. How do we make it quicker? So what we want to be thinking is like, things like numba, these larger conceptual units, right? So this was back in 1977, this quote about the von Neumann architecture versus, freeing us basically from locking ourselves in as programmers to tying ourselves to this kind of mental model, right? So if we can have programming abstractions that aren't built around there, then we can target other types of hardware as well, right? So it frees us from sticking to this kind of sequential computation. And so this, today, we see this in the field with things like numba, with things like Tensorflow, right? So they're no longer, this is a some sort of visualization of a Tensorflow graph, and it's non-sequential, right? There's things happening in parallel, and the other part of it is that it's not tied to some specific hardware architecture, right? It's expressing the domain that you want, and then we're then taking that TensorFlow graph and compiling it to different hardware architectures. So it's trying to take our programming model and bringing it sort of like slightly up a level, so we're talking about our domain instead of talking about how we're actually executing our instructions. And this is complicated. So it's the reason why I think NumPy and SciPy and these things were built as they are is because it's simpler conceptually to just think about, hey, like I have some memory and I want to execute on it more quickly, so I write it in C instead of writing it in Python, right? You get a speed up there, fine. But if you then start thinking about, hey, I have this whole program of all these mathematical operations, and not only do I want it to run on my one CPU, but I want it to run on a GPU or an FPGA or some other hardware that's going to come out next year that I don't even know what the instruction set is going to be like. Or furthermore, it's not going to be a sequential kind of instruction set. How do we build our software around those kinds of optimizations? So because it's harder, I think we're seeing some innovation in vertically integrated stacks, right? Like, so if you say, let me stick to the Google stack, let me use Keras, let me use TensorFlow, let me use JAX instead of numba, then you kind of get this nice world in a way where you can say, hey, I'm just building my TensorFlow graph, and I'll let other people take care of where it's going to run, right? And so it gives users this nice abstraction. And the point here is that these other hardware vendors like Intel, AMD, NVIDIA, all these little blocks are their own languages, basically, or hardware. So things like ngraph or OpenVINO are in themselves their own set of instructions and languages that these hardware vendors have described so that you can run efficiently on their growing diversity of chips. So as a Python user, right, I want to just write my code and have it run on all of these options and more in the future. Right? And as an ecosystem, we need to be able to support having libraries that can run on, so that you have your front-end API that users target, but then that is modular enough to move to new platforms as they become available. Right? Because users don't care about this. They care about, hey, I bought some new GPU maybe and I want it to run faster, or I want to throw some money at this and parallelize it in the cloud. Like, they don't want to care about what IR you're using in the middle to go from my pandas to my output. But as a community right now, they kind of have to care, right? They have to pick, do I import CUDF or do I import pandas? Do I import Dask? And so this is just growing as a community. Sort of the users are now forced to choose a library, right? And this is even more so the case with the deep learning libraries like Tensorflow and PyTorch, where the APIs are incompatible. So you write your whole stack on top of one of these, and then you're now stuck with it. So we have this kind of buy-in problem. Let's take a step back, and let's look at some examples. Well, first we want to say yes. So there's all these great things in Python that we love. And basically, what this talk is about is situating this problem that we want all these things to work, but we want them to work in the future and for the future of hardware and performance optimizations in Python. And then I'm going to look through some specific ways we might be able to think about that. And I was just in Peter Wang's talk, which was about sort of the having instead of having a goals-based approach, having like a values-based kind of approach in open source. And so it helped frame this talk a bit, because it's less about specifically running these things quicker, but it's more about what are the values as an ecosystem that we want to put forward as we make this support for these new hardware and new software, right? So we want things like we want it to be decentralized, right? We want to be able to cooperate. We don't want you don't want to have to work at one company to be able to play in this ecosystem, right? We want to encourage innovation. So if you have some new way of optimizing, you should be able to plug in without causing a lot of pain to users. So it's more so about what is the ethos we want to bring to this ecosystem moving forward, and then how can the technology, it should be supporting us getting there, right? So first, let's just start with the simplest way that we might think about this in Python, and then we can kind of show how that's not enough at the moment. So who here is familiar with MyPy and typing? Has anyone imported these modules? 2, OK. So MyPy is a static type checker for Python. And Python now provides a typing module and a typing extensions module so that you can say, this is sort of like an interface, right? And you can say that my code corresponds to the interface. So it's a concept that's very natural in Python, but this is just a way to be concrete about it. So this is called a protocol. So the idea here is we have some object which supports indexing, and it supports adding. And it supports indexing by integers, and it supports adding with itself to give a new array. So we might say, OK, let's standardize, right? Why don't we all standardize, and let's come up with some great protocol here for arrays or for data frames, and then we can all cooperate, right? That sounds good. So let's see how we'd maybe use this, right? So then we'd have some function that would say, oh, I can take this kind of array, and I can do some kind of fancy operation with it. And then we might want to say, OK, so now let's create an implementation of it. Let's create an implementation that uses NumPy arrays under the hood. So this is, it just forwards the, so you pass in a NumPy array, and it forwards the indexing to the NumPy array and the adding to the NumPy array. And so then we could create a NumPy array with a range. So maybe we should run this code, since we're in a notebook. You create some NumPy array, and now we're, we can call these functions on it, like getItem and adding, and it works fine. So now let's do this with Torch, right? So this is not that exciting, but we can do the same thing with the Torch array. And then we can call the Torch arange. OK, this is all fine and good, but there are some issues here. First, you noticed I had to change the arange function from NumPy to Torch, right? So as a user, you still have to know kind of like what paradigm you're picking, right? And so imagine this arange was inside of this function somewhere far away. Then how do you, as a user, you come to this and say, well, now I want to run it on Torch. So you have to go rewrite your code and rewrite your imports to now use PyTorch instead of NumPy. Right? So that means that there's a pretty big barrier to entry for people switching from NumPy to PyTorch or PyTorch to NumPy, which means it's less likely that we can innovate as an ecosystem if people have to go and rewrite all their imports if they want to try out a new library. Travis gave a talk yesterday on UArray, which is another approach here, which does let you have a global sort of override where you can say, use this context, like use the PyTorch context, and then when I call uarray.arange, it'll use the PyTorch function. So that, in turn, gets us part of the way there, right? Gets us closer. Because now we can have a global context, and you can write your libraries that are just dependent on the interface that we provide, this one, and they shouldn't depend on the particular implementation. But let's see if we can make that a little bit more concrete. So this is a similar interface, but there's no actual definition here. It looks like the protocol, right? It looks like a typing description of what you want. But what we can actually do, so we can write our same function. So we can actually call this on arange, and we get a result. Well, what's our result? Well, it's just the function that we want to execute, right? So it's just a way of saying, hey, before we actually execute anything, let's take a step back. Let's build up everything that we want to do, and then we can decide how we want to do it, right? And so the point of this is that it has a very clean barrier between people who are consuming an API and people who are providing the API. If you're consuming the API like this function, there's no way you're going to know what's inside of those arrays. You can't. So the problem we have with NumPy today is that some people consuming NumPy look inside the NumPy array and say, hey, this is a pointer to a bunch of memory in C, and I'm going to do some fancy stuff on it because it's faster. Which is cool, right? That's great. But then it means you can't use that library with another NumPy array without hitting an issue. And there's no way to, right now those things are tied together, right? So we don't know who's depending on the NumPy API versus the NumPy implementation. And so with this approach, it forces those things to be divorced. Right? If you depend on the implementation, that's all you get. The API, that's all you get. So then you might ask, OK, so what do we do with this, right? How do we actually evaluate it? Before I get there, I just want to show you sort of like how this works internally, because it's pretty simple, even though we get this kind of fancy graph. So I also work on JupyterLab, so I made a JupyterLab extension to show this graph here. So, but I want to show you how this is actually implemented. So I have this expression here. And I can see what function did I call to get it. So I called getItem, right? This was the last function that I called to get this expression. And I can also look at its args. Right, so the two args are the adding and then the 5. So the implementation of this is pretty simple. It's just this expression object is a class that holds 3 things: the function, the args, and the quargs. So it basically just records, right, what you've done. So instead of it's like if people are familiar with MatchPy or other expression systems, it's just like those, but instead of having to write, hey, this is an operator which takes 3 arguments, and the first one needs to be this, second one needs to be this, you just write a Python function, right? And so then you decorate it with this, and then when you call the function, it builds up the expression. So the other way I could have done this is something like this. I just say, hey, I'm making an array. The function is arange. The args are 10, and there are no quargs. right? So this here is the same as doing this. Right, so this is this decorator, this metadsl expression decorator. All it does is it takes this call here, and it creates an array object out of it. Right, so the magic here is really not much, and it's all relying on the typing annotations, which are compatible with MyPy. So you just write the typing annotations, and then it figures out, hey, I'm calling arange, I need to get an int, and the object that it returns should be an array. So you get an array out. So that's all like fine for how to make something, but then what do you actually do with it, right? How do you evaluate it? So in some ways, metadsl is two parts. It's just this first part, hey, I want to make some expressions that are typed in Python using classes and functions. That's a good base for an expression system that feels pretty natural to use. The other part is a pattern matching system so that you can say, hey, I have this graph of expressions, now let me replace it to evaluate it in some way. So let's show an example. Let's say we want to do something similar as we did before, where we have a NumPy array implementing this interface. So we make a function that takes some NumPy array and creates one of our array classes. And so now we can call this if we want, right? We can say, right, so we can call this, and we could say add it, right, because this is what we defined, but we still haven't defined how addition works, right? So we see we have an add call on two NumPy arrays. So now what we should do is we should write a rule that says, hey, if I'm trying to add two NumPy arrays, let me add the arrays themselves, right? So that's what we do here. We say, let's create a number of rules that will execute repeatedly until no more are done, and they'll execute recursively across the expression. And if we set it to the default, then it'll show up as the repr in my notebook. So this is one for arange. So now we made a rule here, so we can say, hey, if I say arange 10, right, it starts out as this arange call of 10, and then this rule executes, and it calls numpy arange, and it wraps that in array from numpy. So the point here is that as you're executing the rules, the types never change. So it still all should type check, right? You still, even though this is an array, this is an array, right? But the constructors maybe change, right? So this is how you would write the execution. Then we can add the other rules for adding and getItem. And then we can take our original expression that we had before, right? And we can see how it evaluates to the result. OK, that's all fine, but we could do that before, right? Like, there's nothing really fancy there. So now what we're going to show is, OK, great. We have this expression system. Now what we want to do is, like what I was talking about before, looking at the larger conceptual unit. So this is what it lets us do. We can build up, say, a string that represents our expression that we want to execute. So here, instead of taking a NumPy array and making it an array, we're taking a string. And so we see that, like, for example, to add strings, we're just doing string concatenation. And then to index, we're doing string indexing. So then you start with something like this, and you end up with just a string, right? And then you could see you could feed this through numexpr or numba or something like that to actually get an optimized result, or compile it to some other backend. Still, this is all stuff we could have done just with our dispatching kind of approach. So the advantage we get here is that we can do higher level optimizations that require building up multiple forms before executing them. So here we have an optimization that says, when I'm adding two arrays and then indexing, index first. Right? So this should do less work, maybe, because we're not having to add the whole arrays. We can just add the one element we've indexed out. And this sort of thing is it's impossible to write right now with NumPy, right? There's no way to put this in the NumPy code base because it doesn't build up an expression at the moment. And so the other thing here is we can look at kind of how this syntax works. So we write a replacement rule. This is the left-hand side. This is the right-hand side. It says this is what we want to match against and this is what we want to replace it with. And the point of metadsl, it doesn't do anything that fancy. It just integrates well with Python. So we have Python types here that it matches against, and this all type checks as well. So you can run mypy over these rules, and it will tell you at compile time, like, is what you're doing sensible, right? Are the right types being passed in everywhere or not? So it gives us a nice fluent interface to write these kind of optimization rules. So we can add this rule, and we can say, hey, now instead of just doing our symbolic rules, let's first do any optimizations we have, and then do our symbolic rules. So we see we can start to build rules into groups and then decide how those groups execute, either repeatedly or in order. So we can see here we have our initial array, and then our optimization runs. And now we're adding the indexed items instead of indexing the added items. And the beauty here is then we can keep all our existing rules. So this would work either with the symbolic arrays or the NumPy arrays, and we can get our result. So the point here is really social, right? The point is that one organization or group can write the array interface. Another organization or group can write a certain backend for it. And then a third can write optimizations. And this is a very simple example here. But the concept is that you don't just have the NumPy array API. You might have a smaller array API that's, a lot of the NumPy array APIs are very similar, right? Like things like zeros or ones. You could say reducing this down to a smaller subset, right? Like that might make sense. So then people who are writing backends don't have to support the whole API. They can just support a smaller subset. So, but users can still use the whole API because why make their lives harder? Why change what they know? So the idea there is that users write for the large API. We write replacement rules that goes to a smaller API. And then that smaller API is what people can target. And so this is a system that you could use to do something like that. Right? So it gives us the space as a community to say, hey, we have the NumPy API, it's great. Oh, cool, well, I have my smaller API that the NumPy API can compile into, and then I can go from that smaller API to other backends. And it lets us as a community each take on those different projects and cooperate without forcing us to all be in one organization or one code base. So just to show another example here, we can say, hey, the repeat operator from NumPy. Let's say if I'm adding a bunch of zeros, I can just remove that. So I just kind of wanted to show that we can match against specific values. So I can say, hey, if I'm adding against a repeating zero of any length, return that just to be that original array. Oops. Right, so then we can, well, hopefully remove out that repeat there. And so, yeah, so that's sort of the concept. And then I wanted to tie it to a few other sort of terminologies or ways of thinking about this, just maybe as helpful if you're talking to others. So the one way to think about these things is domain-specific languages. So one way to write domain-specific languages is to write your own interpreter, right? Like this is maybe like SQL, or if you said, oh, I'm going to go off and write my own syntax and parse it myself. So those are standalone, and you can do those, but they require a lot more work, right? And so this is why we see people like Tensorflow. They're not writing their own language. They're embedding it in Python, right? So we can use all the existing facilities like printing, et cetera, in Python to write our domain-specific languages. And then the difference here between, like, say, NumPy today and this approach is the difference between deep and shallow embedding. So, with the deep embedding, like so here it says, deep embedding, you construct an AST, and the shallow embedding, you evaluate the terms as they execute, right? So that's what we saw in our first example, right? When we just had our array API. It's still a domain-specific language. We're defining our API, but it's shallowly evaluated. It's evaluated directly as we create the terms. They're all evaluated. And the advantage of the deep embedding is that it gives us more room to play with it, right? It gives us a kind of breathing room to say, hey, before we go and execute all this stuff, let's just take a second, to think about what we want to do and make some choices there, looking at the whole program. The other way I've been looking at this recently is about co-data versus data. So I guess co-data is a term from logic, but the idea is that, so here, data is concerned about how values are constructed, and co-data is concerned about how they are used. So co-data is about how they are used, right? So if we have some Boolean operator in Python, how do you use a Boolean? In the end, it all comes down to one statement, the if statement, right? You can construct and anything else out of the if statement. So if we talk about the co-data of bool, it's this if statement, right? So in the co-data of our array was the indexing and the get item. But the data of the Boolean is maybe like the Python bool, right? Or in the array case, a NumPy array, or a Tensorflow array. So by metadsl lets us separate these two concepts so that we can talk very concretely about co-data without mixing it up with all the data. And so this is an example here. We can say, hey, we can say, if I have a true bool, then it should evaluate to its left side. If I have a false bool, it should evaluate to its right side. Right? So then we can start building up these kinds of concepts and executing them. And the point is that co-data lets us talk about interfaces that is in a language agnostic way. So you're not talking anymore about, hey, what's in memory? Like, what's my int type? What's my float type? You're talking about the API in a way that's abstracted away from your particular language implementation. So yeah, as usual, there is no way to open up a higher order function, one example of a co-data type, and inspect the way it was implemented. So the problem with NumPy is that people can open it up. I mean, the problem and the advantage, right? It's fine, it works, but that's the issue, is that people can open up a NumPy object and try to look at what it is, and so that then it makes scikit-learn not work on, say, something that looks like NumPy but really isn't. So as a community, this is like a sort of an idea of, can we be more explicit about our co-data and about defining these interfaces so that when you depend on something, you know what you're getting is just the interface. You're not getting the execution. Just another kind of example of this is, here is how we define Fibonacci. So we can see it looks like, it feels pretty much like Python besides the control flow. So this is one issue with this framework at the moment and Python at the moment, is that you can't override control flow. And this is the same issue that Tensorflow is having, that PyTorch is having, and they're having to write either tracers where you decorate your function, or like Numba, right? Numba has to inspect the IR and analyze the whole IR. So this is sort of a language level issue that I think we could be solved, or hopefully we will solve at the language level, like a form of quoting or some form of being able to say, hey, I have some control flow, but I don't want it to execute how Python executes my control flow, right? I want to build up some kind of expression. And this also kind of shows the difference between this approach and Python. Like, this builds up a graph, which is strictly functional, and Python is very imperative, right? So you do have these, where those things meet, you have some friction, right? So we need, and this is common in the compiler community, you might have one abstraction that's just control flow heavy, and then one that's about data flow. And it's, they're both useful for different things. It's not like one is the end all be all. But in this kind of API conversation, the functional form is much more useful, because then we don't have to worry as much about mutating state, right? So if we can go more easily from Python, this imperative kind of control flow, to this functional control flow, then this will help us build fluent APIs for users, but that compile down to different backends. So this, this works, but it's a little ugly, right? You have to kind of do this functional if sort of thing. Yeah, so I wanted to end on a nice picture of Guido and a quote from him from 1999 for his Computing for Everybody grant, where he said, we're looking forward to a future where every computer user will be able to open the hood of their computer and make improvements to the application inside. So if we think about that chart earlier with Google and the different hardware vendors, I think what I'm hoping is that we can look for a future in Python where people feel empowered to to open up any level of that stack and make improvements or innovations or forks, right? And they're supported to do that by the kind of tooling that we have. So thank you. That was my talk. Happy to take any questions. Okay.
This seems like a really, really brilliant idea. I wonder what the abstraction cost might be. And like when you compile it out, they would get rid of it, right? But how do people run with your abstraction in the middle when compilation may happen behind the scenes?
So so I think maybe 2 parts here. So let's see. Let's go back to this image. So one thing is, we're compiling to these. So we're not handling the runtime in any way, right? We're not saying we're going to have a better runtime. We're just going to say we can get to your runtime that you want, right? And so there is some cost in terms of like optimization, right? Doing all this work is not free. But I think what we can do is we can make those trade-offs in a more like controlled manner. So hypothetically, you have this. You have an abstract way of compiling. You could then compile AOT to something like NumPy, right? So if you look at Numba, right, it has some AOT capabilities. So it's like if you take that sort of idea of something like Numba, but then we say, hey, can we build our whole stack like this? And just the compiled library is just an artifact of our more general library. So then for people who want eager execution, they just want to execute on CPU, fine, same cost, right? I think the cost is an abstraction cost. Like this is way more complicated than writing Python code. And part of that is also the language isn't it's not built for this. It's not how people thought about writing Python code. So I've talked to there's a few other folks working on similar things. So one of the things is debugging is really a pain for this kind of thing. Like you need to be able to match tracebacks if you want this to be useful, so that when the user gets some error, they know, oh, it is generated in LLVM, but really it came from this file over here. So that's an unsolved sort of problem, or I mean, they're in Python at least, right? So it does introduce a lot more complexity. It's not simple. I don't know if that answers.
That's a good answer, yeah. Just having some kind of AOT before you. Well, the AOT is what has to separate the end user. So like there's at least 3 different camps, right? There's the people who are writing the interface. There may be a distributor like Anaconda or somebody like that who would compile it to a particular target thing.
Yep.
And then there's the end user.
Yep.
So yeah, that's fine. That's good.
Yeah.
So this versus your array. Where's the overlap? Should your array be built on this, or will it have this?
Your array is really fast, and it's way less complex. And so it doesn't handle any of the lazy part. So it's a going back to the DSL definition. So it's shallowly embedded. This is deeply embedded. So you can't build up big forms and then do optimizations on them with UArray. I mean, so what we've experimented with UArray is fine. Use UArray. You can use UArray to build up this graph. I mean, that's one possible way to use them together, if they were, say, both used. Yeah. So this also fits with. I don't know how many people are following the NumPy extension story that's going on right now, but there's currently ways to sort of say, hey, I have a custom NumPy array, so that when it goes through the NumPy code base, it calls its methods instead of the NumPy methods. And so this also, it doesn't replace that at all, right? It would fit with it. So you could say, hey, if NumPy supports that, then you could pass one of these objects through the NumPy code base, and you get basically an AST of what you want to compute at the end. So all of the extension stuff going on in NumPy, it's not like this is a, it would rely on it basically if users were to continue using NumPy as is. The one thing that you can't do with the NumPy story is override a range, right? Or they're doing it based on type, so it's all based on type dispatching. So it would be like the type of the int you pass into a range has to be a torch int for it to call the PyTorch a range. So you can't do this kind of divorce there, but yeah. Anyway.
we're out of time. It's
Okay.
a lunch,
Okay.
but if everyone wants to save
Good.
one more question, I think that's fine.
I guess I wanted to ask, with your optimization, how much are you going to be able to capture optimizers like LLVM or Numba or all this existing knowledge,
Yeah.
rather than requiring people to re-implement it for their particular domain?
That's a great question, and I think that's the kind of conversation we should be having, right? And we should be having it through building these different, IRs, sub-languages, and seeing how to translate from one to the other. Because that's when really the collaboration gets unlocked, right? When you can say, hey, I have this intermediate representation for arrays that does a bunch of optimizations, and we can share it now across backends. And this is what Google is doing with MLIR. I don't know if anyone's familiar with that, but it's a meta IR that they're using for LLVM and Tensorflow. And it's a similar sort of idea as this, but it's in C++. So I think if we can move to answering that question, then we'll be in a great state. Cool. Thank you.